Well, good morning, good afternoon, good evening, whatever time it is for you. Welcome to Data Movement and Computational Storage. This is a panel discussion sponsored by the Storage Networking Industry Association's Compute, Memory and Storage Initiative. Say that all 3 times fast. My name is Jim Pfister, and I will be your host today. Now, you could stare at these static pictures of us, but rather than that, let's all wave. So I'll introduce myself. My name is Jim Pfister. I will be your host and moderator today. I'll go in order of who will be speaking today. Ellie, why don't you go first?
Hey, good morning. Ellie Tiomkin. I'm the SNEA Computational Storage Special Interest Group Chair and also work at NGD Systems.
All right, and Nidish?
Hi, I'm Nidish. I'm part of the strategic marketing team at KIOXIA and architect focused on SCM, computational storage, and emerging interconnects. Nice to meet you.
SCM being storage class memory, correct?
Yes.
All right. Great. Part of the fun of the moderator is making sure I do all the acronym checks. And Mr. McIntyre.
Hi, I'm David McIntyre. So I work over at Samsung, where I lead product planning and business enablement focused on computational storage.
All right. So we are excited to be with you today. Let me give you a little bit of just housekeeping stuff. For those of you new to the Bright Talk platform, you have a couple of buttons underneath your viewing screen. One of those will take it full screen. One of those will allow you to download content and slides. Another one of those will enable you to ask a question, and we certainly enable you to ask, or certainly encourage you to ask questions today. I'll be asking some as they go through, and we've got 3 very brilliant presenters and 1 moderator. And so let's make sure that you're asking good questions. So none of us on this call are lawyers. We are not intending to give you any legal advice. There's no warranty expressed or implied, and we would advise you to use this at your own risk. This presentation is a project of SNEA. This is copyrighted by SNEA, but although you do have SNEA members do have fair use, and you do have the ability to quote and utilize this as necessary. If you're not familiar with the Storage Networking Industry Association, we are 180 industry-leading organizations with about 2,500 active and contributing members, and we reach over 50,000 professionals worldwide with some of the activity that we do. SNEA is a nonprofit global organization. We're dedicated to developing standards and education programs to advance storage and information technology. You can see that we've done several technical positions, ISO standards and ANSI standards over the years. And the Compute Memory Storage Initiative is a community of storage professionals and technical experts who are supporting storage, new memory architectures, and new compute architectures. So we will be talking today about computational storage. Let's start off by talking about what is computational storage and what is data movement. So Ellie, I will hand it over to you and let you go.
Thank you, Jim. So hello again, everybody. So the subject today is data movement and computational storage. And let's first go a little bit over some of the definition. So we are all aware of the data growth and data growth projections. Every research organization is projecting different number, but they're all humongous. And it's interesting to see that as the cloud is anticipated to grow at scary rates, there's an emerging growth at the edge. I think that Gartner is predicting that by 2025, a third of the data that is created will be at the edge and not go all the way to the cloud. That compared to about less than 2% from last year. So very interesting phenomenon that is going on. And as this huge amount of data is being created, one of the question is, how is that data moving from one place to the other, and how compute is going to be applied to that data. So moving to the next slide, we look at the current architecture, right, the standard x86 architecture. And when we look at it, the 3 major components of every compute architecture is the CPU or GPU, the memory, and the storage. And what we see is that as data grow, there is a bottleneck. Data is being stored, and now whatever you need to do with that data, whatever type of application container requires you to move the data back to the host in order to make the computation, run the application, run the container. And that bottleneck is a problem. And that's where computational storage comes to help and alleviate some of the pressure from the host CPU. So going back to the high-level data movement scheme, if we see here where the data is created on the left-hand side from the things to the edge compute system, unit to the cloud, it is obvious that all the data that will be created will not be able to move from that edge compute unit to the cloud, which means that there will be a need to run compute at the edge. And if that compute at the edge is being run on a CPU, then we run into the same bottleneck of the compute paradigm that I just described. So applying computational storage at the edge, not only at the cloud, it seems like a natural way to solve the problem. So SNEA defined 3 different classes of computational storage devices. The first one is the computational storage drive. It is an SSD or an HDD that enables compute locally, usually by either implementing an FPGA or an ASIC that are dedicated for that job, either doing both the storage function and the computational storage, or a separate SoC and FPGA. The different class is the second class is the computational storage processor. Here we have a processor unit, again, either an FPGA or ASIC based, that sits on the fabric of the storage, but is only dedicated to run compute alongside the actual storage devices, HDD or SSDs. The last category is the computational storage array. Here you have an array that is combined of HDDs, SSDs. Some of them may have computational storage and some not, and all that unit is there's a controller that manages the unit as a whole and alleviate the host CPU with the processing.
So Ellie, really in this case, you're not defining the amount of compute or the amount of storage in any of these devices. You're just saying that this is how they can be architected in order to support this. So I could actually have a pretty powerful computational storage drive that might mirror a small array or something like that, depending on the amount of compute and storage and the cost that I put into that, correct?
That is correct. So this is the high-level definition of SNEA, and the actual compute power that you have in each of these categories, it's really up to the company that designed the solution. So, and there's a lot of things to consider when you do design. Let's take, for example, computational storage drive, right? So, is it going to be an FPGA or an ASIC? What type of core are you going to implement? Will affect how much power you have for compute and how much power the device draw from the system. So there's a lot of things to consider, and then it's really up to the vendor to decide what type of compute to implement based on the market that they're going after and the solution that they're trying to improve.
Okay, excellent. Thank you.
Sure. So going back to that original compute paradigm, we have the CPU, we have the memory, but here we have SSDs that each one of them, SSDs, HDDs, computational storage devices that now have local compute capabilities. So regardless of the amount of compute that is on one individual device, now we're taking advantage of distributed processing. Because the more computational storage drives you have, the more compute you have as a system. A lot of minions trying to help the host CPU to handle the processing as a system. So the idea behind computational storage is to take the compute function, move it to the storage, but with no intention to replace the host CPU or GPU, but to enhance it, augment it. So as a system, Less data is moving between the storage and the host, means better system performance and lower system power.
Mhm.
So looking at the computational storage view, we see that the compute request is initiated from the host to the drive execute that request and move only the results back to the host. And therefore, there's a massive reduction in data movement and by using less power as well. And some type of application, it can be in the cloud, can be running databases, running storage functions such as compression or encryption, or running things like databases, AI, machine learning on images or videos. And the user cases really go way beyond that to things as even low Earth orbit, small satellites, even cryptocurrency. We see now Chia, there's a big hype around Chia for capacity plotting and farming, where computational storage can provide value in that plotting scheme by enhancing the process. So lots of use cases for computational storage. It's really up to the end user to define what they're looking for. And as a rule of thumb, the larger the data set, the more use and the more efficiency computational storage will bring.
So really the value that comes into this is both latency sensitive. So I have the ability to make decisions faster at the edge, but I can also then distribute my computing so that I can process decisions anywhere. So computational storage really serves a variety of functions, but all of it is really in terms of improving the decision capability by bringing the compute to the storage. Is that how you'd characterize it?
Yes. Yes, you bring the compute to the storage, you improve the latency. That reduction in data movement bring as a system higher level of efficiencies in terms of performance and reduction in power. That a standard compute system where you move the data every time you need to make use of it from the storage to the host, that action of moving the data back and forth, nobody's really measuring the power cost of that action, because this was the standard. However, now when you do have computational storage and you can run some of the application without moving the data, there's a massive reduction in power, and especially with the anticipated large growth in data, that's going to be something very important in the future.
Excellent. That's a great overview. Thanks, Eli.
Thank you, and I will move it to Nadish.
Thank you, Eli and Jim, both for setting the stage for this part of the talk. In this part, join me in looking at how computational storage, or CS in short, enables flexibility in compute systems, and what benefits from these additional options accrue to the deployed systems. First, storage systems and device vendors have always provided limited acceleration features as part of their products. We have always done that in the past. So what sets the current generation of computation within storage apart from earlier offerings? The answer is programmability. Programmability is a giant stepping stone in promoting the use case experimentation by the end user. When customers experiment with how stored data can be efficiently processed using computational storage, they end up creating new paradigms in IT systems in architecture. So in analytics on huge data sets or edge use cases, this programmability and compute capability even opens up new pathways. Predictive maintenance and retail operations optimizations are two examples of such use cases.
It's interesting. It's interesting, Adish, because back when dirt was young, and I was originally getting into the computation business, it used to be that your processing transistor count was significantly higher than your storage transistor count. effectively what you're saying here is now that that's flipped, you can basically put that programmability anywhere in order to gain benefit from it. Would that be a good characterization?
That is right, Jim. I mean, the main focus here is to move the compute to that point in the system where it can achieve the work with minimal amount of overhead in terms of power consumption or network bandwidth. So one such feature that computational storage enables is moving the compute to where the data sits at rest. And with the ever exploding size of data sets, you can see how this argument can quickly gain weight. I do want to stress on the design and upgrade cycles as well. So traditionally, storage systems and devices have had a multi-year design and upgrade cycle. And having these storage devices programmable in order to enable compute offload speeds up the design cycle by moving the point of redesign, if you will, to the end user. So I will draw on two technology trends in the recent past to further emphasize this point. First one I would like to show is graphics cards. Graphics rendering cards started out as fixed function data pipelines and then evolved to programmable graphics shaders, leveraging languages such as OpenGL, and today can even be used as general purposes or GPGPUs with OpenCL and CUDA. Similarly, the mobile phone that started out as cumbersome bricks with limited GUI options, if at all, eventually evolved to an all-engaging user platform, the smartphone as we know it today. This transformation was set in motion once OEMs, carriers, and middleware providers in the mobile ecosystem realized that programmable platforms provide the best way to enhance the diverse experience of billions of mobile customers. In the mobile industry, this programmability even created a new form of marketplace, for example, the App Store or the Google Play. So I'm envisioning that for storage devices, the programmability given by computational storage will open up all such avenues for the end user and the OEMs and vendors. Next up, let's see how this programmability can play out in the storage space. The SNEA Computational Storage Technical Working Group, or TWIG for short, was started with a charter of integrating compute functions with storage. In the TWIG's work, the architecture of these reference libraries that are being defined are being done with an eye on interoperability with other storage standards. Prior to offload capability in storage, SSD and HDD vendors have provided limited functionality such as compression and encryption on a device level of abstraction. Furthermore, such solutions would use rigid vendor-specific schemes and have limited deployment flexibility. Going up a few levels in the storage vertical, storage systems and adapter cards provide functions such as deduplication, erasure coding, and RAID. Computational storage simplifies the implementation of these functions, providing sufficient flexibility to address new use cases, while reducing the development cost incurred by the OEMs to support this. One example is the implementation of media or content-specific compression algorithms for select customers, similar along the lines as what was enabled by Microsoft and Facebook. The scale-out or distributed nature of storage resulting from the quantized SSD and HDD capacity points can be naturally exploited using computational offload. By doing so, we can derive insights from at-rest data, just like Ellie mentioned, by using these CSDs to perform indexing and querying functions. So it moves us to the next step in the evolution of storage, which is gaining insight from the stored data. In the case of power-constrained edge deployments, programmable storage streamlines the inference and data processing pipelines and helps the solution meet the necessary power and location-specific constraints. So let's move on and see how the SNEA twig enables this revolution. The main ingredient is the storage API, currently being drafted in the CS twig. The storage API performs a form factor or implementation agnostic method of discovering, configuring, authenticating, and deploying computational storage entities in the system. Some examples of such entities are the CSD, CSP, and CSA that were described in Ellie's talk. A user space library definition and reference implementation is also in the works and is designed to improve performance and usability as opposed to a specific OS-targeted release. During the definition, twig liaisons to various standards organizations such as NVMe and T10 work to ensure that the API and the library calls map to native commands, processes in those standard definitions, thus minimizing overhead in device implementations. One such example is the eBPF-based offload command scheme that has been proposed in NVMe and is also incorporated into the CS API definition. The twig's work is also compatible with a variety of storage addressing flavors, example LBA-based versus KV-based, and also media with different characteristics such as flash, persistent memory, also formerly known as SCM, hard drives, and tape. Let's go one step further and see what this means for system design. The increased flexibility in storage comes with its own additional opportunities. Systems can service a wide range of design points based on compute and energy needs, ranging from racks and pods in data centers to edge or remote deployed units, which are power constrained. This underlines the need for a robust, well-specified monitoring and configuring API, as well as a tolerance to failure of the offload entities. The SNEA CS API anticipates these requirements and has built-in monitoring and control hooks to dynamically add, remove, reconfigure offload-capable systems. The dynamic nature of the workload in such compute systems is also being studied in academia and open source forums. One such example is the uSocial Storage project. This is a research project at the Center for Open Source Software, CROSS, in UC Santa Cruz, that aims to develop objective measures of the trade-off between moving data across the network or I/O for processing versus in situ processing of the same data at the storage device or node. So just to stress on what Ellie was mentioning further, in addition to providing a lowest power implementation for a compute problem, there is also the overarching need of figuring out when that would be the right solution for a particular offload. So this U-social storage research focuses on that. KIOXIA is proud to sponsor this work at CROSS, and I welcome you to learn more at the URL shown. While you are reviewing the U-social project, do check out the Skyhook research project as well. That focuses on dynamic remapping of stored data to different data formats as needed based on the incoming client requests. So this gives you a flavor of the enormous amount of opportunity in terms of research and system architecture potential that is enabled by the flexibility from computational storage. As it must be clear to you by now, the computational storage paradigm opens up the floor for a lot of innovation, not only for end user applications, but also in terms of system architecture, both at an individual node or app level, and also at a cluster or data center level of abstraction. The SNEA twig is laying the groundwork for such innovation and invites system architects and application software gurus to join the movement and innovate using computational storage. This concludes my portion of the talk, and I will now hand over the talk to David McIntyre from Samsung, who will dive into the security aspects of computational storage.
So I think the key here that I heard was the technical working group, as well as the special interest group that does marketing, which Ellie leads, are still open to having more participation. And so certainly anybody listening or anybody viewing this podcast later is more than welcome to work with SNEA, and we'll have some more data on that. Now, David, I think there's good news and bad news. The fact that we're driving compute storage makes it allows the storage to be a lot more intelligent, but it also opens up a whole new avenue for threat levels. Is that true?
Yes, it is. We're basically introducing a new component into our system, so we need to deal with that as security issues continue to ramp. We need to be proactive and ahead as best we can of those issues with SNEA and also with across the industry. And it's an opportunity for we folks in computational storage to define what those security risks may be and address them before they happen. So with that, so my two esteemed colleagues gave a really nice job on the overview of computational storage, and basically that left illustration shows how we're able to reduce bottlenecking between the CPU and the host and the computational storage drives that you see below, and by providing in-situ processing at the drive level. But let's focus at the right-hand illustration, which we're talking about examples, applications, deployment use cases, and this is where security needs to be addressed. So for the first case, that's the standard model that we just went through, where you have the host talking to one computational storage drive or perhaps a series of them. And so from a security management standpoint, we need to be cognizant of threat use cases, both at the host level, the networking level, and at the storage memory level. The next category would be the smart cache layer, where here the computational storage drives provide high performance storage and localized compute capability as a layer. Think of a wedding cake where you have your hard disk drives below, providing more of the standardized storage capability. And then the next layer up would be higher performance storage and solid state drives, perhaps with some storage class memory or memory resources within. And they're providing higher performance, lower latency to the host complex. So that's another layer that we need to address when we're considering security issues. And lastly, Eli was mentioning that there is this explosion of data occurring where we're expecting edge ecosystems to grow exponentially. And therefore, it's important for us to address any security threats and resolutions across the entire ecosystem from cloud to edge. So let's spend some time on this diagram because I think it's really educational on a number of the threats that we need to consider. So when we look at risks versus standard storage with computational storage, we know that the CSDs may delete, they could add, they could modify data on the drive to prepare that data and compute on that data and then send it back to the host. That the CSD also can be programmed with an FPGA where it can download specific acceleration algorithms or modifications of those algorithms. So that's another security inflection point. And then also virtualization, where you're able to virtualize CSD resources as well as compute resources. That is also a security issue to deal with. So if we look at these blocks within the illustration itself, we have 5 blocks down below and 3 on top. So the 3 on top represent the host processor complex. And here we need to be able to address the host agent to CSD authentication and be able to communicate directly and manage the security between the host complex and all these 5 blocks down below. So what are these 5 blocks? Well, on the left, we have our traditional storage devices. These can be just your standard hard drives or solid state drives, where you typically have a storage controller and then the storage media within. The next block over, that's the computational storage processor. So here really we're illustrating adding an additional processing component at an endpoint position, which is complementary, as I believe Eli was saying, versus or with the host processor complex. So it's basically another compute element that offloads some of the traditional processing that the host would perform. The next block over is the computational storage drive itself, where you're basically building upon the previous 2 blocks, and now you're adding not only the compute element, but also, of course, you've got the storage controller and the storage media underlying elements. So, and then if we move to the 4th block over, well, now we're integrating both the computational storage drive and then access to that computational storage processor next to it on the left, and as well as some, it could be direct attached storage. So, and then finally, just for the overview here, we have an array of computational storage drives that are interconnected just to build out in both compute and storage capacity. So what does all that mean? Well, it means that you now have all these insertion points for security threats, where before you just had your cluster of drives connected to the host complex. Now you have compute elements, you have computational storage processors, you have storage controllers, you have arrays of computational storage drives. These all offer up threat opportunities to a bad actor. So it's important for us as a development community to ensure that the data is adequately protected across all these different permutations. So what does that mean? Well, first it means that the SNEA computational storage twig is proactively defining an architecture that does keep security as a priority and in mind. So security functions to consider would be, I mentioned authentication between the host agent to the CSD, authorization, so this would be secure data access and permissions only for those entities that need to have access to the data, encryption, so encryption blocks, encrypting data mechanisms, and then auditing So ensuring that before and after secure logs show that the system still was robust from a security standpoint. The other thing to consider is risks versus external accelerators, such as GPUs or FPGA cards. For computational storage, you're actually providing direct access to the storage. So you're going to decrypt the data, compute on it, and then encrypt it and send it back out. There is also, as in the case of an accelerator, FPGA programming concerns. So there has to be means of having secure programming available for the FPGA programming. And then also the CSDs will have access to network infrastructure such as NVMe over fabrics. And so this slide gives a nice overview of many of the considerations we need to take into account.
So really in a lot of cases, the first thing that needs to be addressed is is basically just the surface area of your threat plane is now significantly bigger. But it sounds like there are some new potential threats that are coming in as a result of this.
Yeah, I think what's happening is not only are we adding additional threats, but also we're compounding those threats because you can have different variants that are building upon each other. As an example, as you're shipping data down to a computational storage drive, and we talked about decrypting that data, well, that's an exposure point before it gets computed upon and then stored or sent back up to the host. Whereas before, you would just do that process up at the host in a safe environment. Now we're going to provide a safe environment with a CSD, but we do have to contend with these additional steps. So this security considerations by cloud service providers, what does that mean? Well, the hyperscalers, the cloud service providers have always had security policies in place. And from an ecosystem standpoint, it's important for us to understand and talk their language. And what do I mean by that? Well, so these policies that the hyperscalers, the cloud service providers develop, they have specific categories that we want to ensure that that functional diagram that I showed in the earlier slide, it supports these sorts of conditions. So whether it's data in flight between the host and the CSD complex, you're going across a network, so you better have proper security measures in tow. Processing requirements in data handling, that the interchange between the in-situ processing that happens on the CSD and how that data is encrypted, decrypted, and is it done in such a way that it's robust enough to support the application and the policy requirements. Buffering and caching across the memory within the CSD. So there could be DRAM, there could be storage class memory. All that needs to be played and considered. And also the CSDs themselves, as I said, can act as a smart cache. So again, that has to be taken into account from a security standpoint. Data at rest, once the data is waiting to be processed or is just simply stored, what is that policy that needs to be addressed from a security standpoint? And there's a few others. Containerization, meaning that if the CSD is performing a specific or a small set of functions within its domain, ensuring that proper security policies are being adhered to in a containerized situation. Same with virtualization or multi-tenancy, where you have many customers tapping into a cloud service provider's service. You want to ensure that you have to ensure that the underlying hardware, the firmware, and the software that manages all those functions and devices are being properly secure. And again, edge deployments is going to grow exponentially for computational storage. And with that comes a whole heterogeneous ecosystem that needs to be addressed as well. So these are key points that we need to address for not only our customers, but our customers' customers. And then on this chart, this is I gave a security presentation just a couple weeks back, but this is a nice summary slide on some of those key attributes that we need to consider from a security standpoint. So root of trust, that means that the devices that are within the computational storage drive are properly protected. That could relate to Microsoft has Cerberus, which is a root of trust ecosystem where you have secure boot across each of the components within a subsystem. So also Google has OpenTitan, and Intel has their own variant of root of trust as well. Moving over to the right-hand cryptography section, here is where you can have a series of encryption blocks. AES 256 is a very well-known one, and these various standards from NIST to FIPS 140-2, these are important attributes as well to consider when we are encrypting and decrypting the data in a computational storage drive. The third place would be secure enclaves, where you're actually protecting the whole subsystem, in this case, a computational storage drive, from sideband attacks, which is a fascinating area where you can actually enter through the power management system and to track keys. Well, the secure enclaves defined by NIST, OCP, and Microsoft, this is another security measure that can be put in place. Self-encrypting drives, either at the drive level, a volume of drives, or at the host, securing specific volumes of drives. These are all variants that are available to us. Number 5, key management. This would be securing specific keys on specific drives, refreshing those keys, restricting the user access to those computational storage drives, and different variants. So key management is also a very robust encryption strategy that's in place today. And then finally, the security lifecycle from the inception of that computational storage drive, the building of the product, the release of the product to production, and suggesting in the cloud service provider data centers, all the way through end of life, where security basically runs alongside each of these phases of a computational storage drive's life cycle. So I think the message that you have now is that when we're looking at data movement, let's all put on our security hats. So data moves across compute, storage, memory, and network systems and devices. So we need to basically go through our audit and check to make sure that we're adhering to proper security measures. So design and deploy with holistic security solutions in mind, not only at the device level, but across the whole subsystem, across the application, and also thinking about and addressing what our customers want to see from a policy standpoint. Most importantly, participate in the SNEA computational storage twigs, where many of these forethoughts are being put into place today, both in the architecture spec and in subgroups, so that we stay ahead of this problem and address it aggressively. Contribute to industry use cases that should be considered for security issues and resolutions. I've touched on that slightly here. Basically, it's fine to design the hardware, the software, the subsystem, but always keep in mind those applications that will deploy such an infrastructure, and will that bring a new set of bad actors or insertion points for security. And then finally, attend SNEA compute storage and networking events and think security always. And that's the end of my section.
All right. I'm going to switch us back to the panel view here for a little bit. So glad that we're all back and still smiling. I just had a couple of questions, and I can throw them out. one, we talked a lot, storage has really always been about data at rest. And data at rest, continues to have value because you want to make sure that you have your data. But computational storage really is saying even data at rest doesn't need to be restful. I have the ability to do more with it. I have the ability to better secure it or to better analyze it. I mean, talk about Ellie. I'll throw this to you to start. Talk about what you really think that means for data in the future with the advent of computational storage.
So, looking at Dave's presentation, I completely agree that there are new security threats and things that we need to consider because of data movement and computational storage. However, there's one angle that I think was not mentioned, that one of the risks in terms of security is when the data is actually moving. And computational storage reduces the data movement significantly. So there are also some aspect that computational storage can play as a more secure way to treat the data, because it is not moving as much and the ability to incept it is lower. And there's also the option of actually using some of the compute core inside the SSD to enhance the encryption and the security scheme. And there are several different ways to do that, and it's to be determined by the actual vendors who implement it. But it's definitely should be in everyone's in mind the thought of how we're going to integrate these new technologies and new standards, but not to jeopardize any of the security of the data.
Mm-hmm. That was a pretty good job of putting on your security hat, Ellie. I mean, you were listening to what Dave said. Dave, any reaction to that?
I was listening.
Yeah, that's very impressive, Eli. So I would say that, and this just came to mind, that if you look at metadata and cache, the data could be at rest, but it could be timed. If it was bad data, that was a threat. So security threats just don't always happen at the same time. They could happen. There could be a waiting period, and that could be done intentionally. In fact, we're working with a cyber forensics company that has educated us as a development platform company that there could be a waiting period of months before an attack actually occurs, and that's done intentionally. So that needs to be also considered. I mentioned metadata is one. They could basically be an insertion point for applications, but things look well at one point in time, one epoch, but months later, you could actually be exposed to an attack. So this would be more of an application consideration that should be taken from a top-down, holistic perspective.
Mm-hmm.
So,
okay.
Yeah. If I may add to that, actually, you're right. I mean, trying to unlock the value of at-rest data actually brings not only new security problems, but compounds the existing ones. One other point I want to mention, especially in the recent time, is the movement towards privacy, data privacy, keeping medical data pristine and away from the wrong hands or wrong eyes. And the computational storage allows you to lock that data and only process it when and if needed in an authenticated and secure fashion. So that's another problem that it can naturally solve without having to build an entire system infrastructure around this.
Mm-hmm. To some degree, you actually have the ability to implement multiple policies in multiple areas with computational storage. So I could actually set a policy from the cloud to an edge system in terms of encrypting certain amounts of data and how it could be used, while at the same time being able to set different rules on the edge on how I want to use it. So this really opens up a lot of great, significant policy changes or policy implications for both enterprises and cloud alike. Would you all agree?
Yeah, definitely. I think there can be various layers of encryption or various layers of compression added on to the data or metadata. There's also this research on fully homomorphic encryption, which allows systems to perform computation on encrypted data. So think about a Facebook use case or a social media use case. You have your profile locked up in an encrypted space, and you want to search across all such encrypted profiles to find something of interest to an advertising client. Having fully homomorphic encryption implemented on the CSD would actually help this use case, because you wouldn't have to pull all those profiles up to the host for processing. So I totally agree with you, Jim, there.
Very cool. Any other thoughts on what we've all discussed today? Any of the three of you?
Yeah, I would think that, you know, in the old days, whether it, you know, at a semiconductor level, it's all about capturing the design win. But I think to provide value, we have to go far beyond just the features that we're providing. We have to actually understand the ecosystem that device is going into. Sure, it could be going into a subsystem with limited functionality, but computational storage, as we're pointing out here, we're becoming the front line within edge applications and the management of those edge infrastructure pieces up to the cloud. So I think for to be competitive in this marketplace, we're going to have to really embrace the existing cloud policies, and also be with our customers on developing the how those policies now migrate or simply change to the edge. And frankly, I think since the edge is a continues to be an emerging market, we're just at the infancy. That there's an opportunity for us to actually partner with our customers, and I'm sure take their leadership from a policy development standpoint, but also contribute in doing so. So it allows us to raise our game.
Excellent. Ellie, any final thoughts?
Yeah, I agree with my colleagues. I think that the infrastructure of data and data movement is going to drastically change in the future as edge emerges and as cloud continue to grow. And utilizing computational storage can be extremely beneficial in this new infrastructure. And we have to work together as an ecosystem and under SNEA to make sure that we're all aligned to provide the right solutions to the customers.
Yeah, and that is a great encouragement, Ellie, in terms of what we really need. So first of all, I'd like to thank the audience for submitting questions as necessary, and for help and for viewing this podcast. Please make sure to rate the webcast. That's one of the buttons underneath your screen there. The link to this webcast and the PDF slides are posted at the SNEA Compute Memory and Storage Initiative website, and you can see the link there. And you can find this webcast and many other topics and videos and presentations in the SNEA Educational Library. There's a lot of really good content in the Ed Library, and I think you'll really enjoy perusing that. We will be doing a follow-up Q&A, and that will be at the SNEA Compute Memory and Storage blog. But certainly, if you want to learn more about this, or if you want to contribute, we would encourage you to join the CMSI and join the Computational Storage Twig. You can see all the links here, snea.org/CMSI. You can follow us on Twitter. You can read the blog, check out the videos in terms of the weekend playlist that we do. We have a lot of material and a lot of capability that you can use to address these questions and more on computational storage. I would like to thank the three panelists for participating today. I would like to thank you all for viewing as well. And I certainly appreciate all the questions that have been coming in. Just one real quick one in the final. We did have one more question come in, and we got a couple of minutes. In your discussions with customers, how dynamic do they expect sets of code running on computational storage to be? I mean, obviously, with the extremes being, codes never changing to being different for every operation, the fact that I now can run mixed code on my computational storage processors really does open up different options. So, what are the customers really telling you? Ellie, I'll go to you. You're a startup in this environment. Usually, your customers are probably asking a little more. What are they really asking from you in terms of the ability to run flexible code?
So the request that we get most often is around the programmability model. Customers want to have a simple, straightforward, seamless programming model that will enable them to run one application, two applications, whatever they need, and change it in an easy way without disrupting the system. So that's an area where we've been putting a lot of focus on to make sure that the programming model is as seamless as possible and transparent to the user.
Nidish or David, any additional thoughts?
Yeah, thank you, Ali. So I will give an example of one of the high performance computing / scientific research client that we've talked to. So this is a high energy physics lab in Chicago. They generate like 20 terabytes of data per day, which goes locked up into a write buffer, then eventually ends up being triaged and moved to final storage. The challenge that the researchers have there is that how do you go through even the triaged data and figure out events of interest? For example, particular particle interactions in the experiment, and zero in on those critical ones which can help in the discovery. And one of the challenges they had was they have the data pipeline pull the data out and it had to be reformatted. So if it was a file or as an image, it had to be converted to one of the formats that the new data engines would understand. For example, an arrow format, as some of the industry participants might know. And doing this reformatting on the fly on this vast store of data was a challenge until we figured out, okay, why not move that reformatting as part of the compute node, the storage node functionality. So as the data is being read out, it's being dynamically reformatted to the correct one requested by the client app. And that speeded up the process of going through these various images and data and zooming in on the right particle interactions. So definitely dynamic reconfigurability, reformatting is essential in some of the cutting edge deployments.
I'll just quickly add that the heavy lift comes into play with the application and the system integration. That's where the real work plays with computational storage.
Absolutely. And one of the things that we like to pride ourselves on at SNEA is that we end before the top of the hour so everybody goes. So the four of us will all wave goodbye. Thank you very much to the audience for participating, and we hope to see you at a future SNEA webcast. Have a great day.
Thank you.
Thank you.
Thank you.